Okay, so this lesson is about standard enthalpy of formation. Exactly what that means will be made clear a little bit later. So this is another strategy that we can use to solve for enthalpy without having to do the equation flipping that we have to do with Hess's law. So first of all, what is standard enthalpy of formation? That's a mouthful of words. The symbol for this is delta HF with the little circle, the degrees symbol. So what this is it is the change in enthalpy, so hence delta H, that accompanies the formation of 1 mole of a compound from its elements in their standard states. Well, so you're probably thinking, okay, that doesn't help. What does that mean? Let's break it down. So it is the change in enthalpy. So it is an enthalpy, it's delta H. What is this enthalpy for? Well, it is for the formation of a compound. Formation means to make the compound from its elements, like elements on the periodic table. You can take whatever compound, you can look at what it's made of, and the formation will be just to make that compound from the element that you can have on the periodic table. Not only is it the elements, but it must be the elements in their standard state. Okay, so what's a standard state? A standard state is the state, solid, liquid, gas of a compound, or sorry, of an element at SATP. SATP stands for standard ambient temperature and pressure, which is 25 degrees Celsius and 100 kilopascals of pressure. Basically, a nice day outside. If you look at the periodic table, a good periodic table will color code it so that you can clearly see the standard state of all the elements. So in the picture here, in blue are the solid elements at room temperature. In yellow are the gaseous elements at room temperature. And there are only 2 liquid elements at room temperature, which is 25 degrees. So that's what we mean by standard state. So you have to check with the periodic table to figure out, is it solid, liquid, or gas? So back to the definition. Not only do you have to form a compound from its element in their standard state, you can only make 1 mole, exactly 1 mole of that compound. So the standard enthalpy of formation refers to the enthalpy that accompanies the formation of exactly 1 mole of a compound from the elements in standard state. All right, so let's look at some examples of this. We can use standard enthalpy of formation to calculate delta H. All right, how do we do that? Well, we have to use it in conjunction with Hess's law. And Hess's law, if you recall, we learned yesterday, if you add up all the individual enthalpies of the smaller steps, you would get the overall net enthalpy of the overall reaction. All right, and today we're going to basically find the enthalpies of formations using a table. Okay, and then you will find some equations and some values on the table, and those will help you solve your problem. So example, the first example, you have methanol, SCH4U. Okay, how do you make ethanol from its elements? The formation of methanol. So that is from carbon, from oxygen, from hydrogen, right? If you just look at methanol, SCH4U, you have carbon, you have 4 hydrogens, and you have an oxygen. So to make it from its elements, you have 3 different elements. Carbon, solid, that's the standard state. Oxygen is a gas in the standard state, and hydrogen is a gas in the standard state. And notice that oxygen and hydrogen are both diatomic, O2, H2. There are 7 diatomic elements, you have to know that. And you have to balance the equation in a way such that the methanol has exactly 1 mole, because the definition says 1 mole of a compound. So you have to divide everything until methanol has a coefficient of 1. So that's why oxygen has a half. Normally you just multiply everybody by 2, but you have to have 1 mole for methanol, so hence that's the equation. And you will have a value for the enthalpy of this reaction. So this will be the standard enthalpy of formation for methanol, and the enthalpy is negative 239.1 kilojoules per mole. Okay, so it means to form 1 mole of the substance, you have an enthalpy change of negative 293, 239. And another example, let's say aluminum oxide, Al2O3. What's it made of? Well, it's made of aluminum and oxygen. All right, so aluminum is a solid, plus oxygen gas, you get aluminum oxide. And of course, you make 1 mole of this, so you divide until aluminum oxide has exactly 1 as a coefficient. So it's 2 aluminum plus 3/2 oxygen, you get Al2O3. And the standard enthalpy formation of aluminum oxide is exactly negative 1,675.7 kilojoules per mole. Where can you find this information? I posted a table way early, like I think the first day of class, I posted a data booklet. And in that data booklet, one of the tables is the standard enthalpy of formations table. So you should have that table in front of you when you are doing the test, the assignment, and even in class, so you can refer to it. So you can just pull that up from Google Classroom. In that table, you will have a long list of different compounds, and basically all of the questions that you see on the test or assignments will be from that table. All right, so you're going to find it somewhere. So let's actually do an example here. So example 1. You have the formation of hydrogen and carbon monoxide gas from water and graphite. So here's the equation. H2O gas plus solid carbon. You get hydrogen gas and carbon monoxide gas. So the question is, what is the enthalpy of this reaction? All right, that's it. That's the question. That's all you have. So you might be thinking, wait, how do I do that? I don't have any numbers to work with. Well, yes, you do. You have a table. So to answer this question, all you have to do is look up the formation equations for each of the reactants and product in this balanced equation. All right, so you have water as a gas, solid carbon, gaseous hydrogen, and gaseous carbon monoxide. So if you pull out the table, you just look until you find each of these. Well, first one you look for is the water one. Notice that on the table, there are 2 formation of water. One is water vapor as a gas. The other one is liquid water. They have different values, so make sure you look at the right one. In this case, we want water vapor. So it's this equation right here. Look on the table. You copy the equation down and check out the number. It's negative 241.8 kilojoules per mole. That is for H2O. All right, and that means it takes, well, it releases this amount of energy if you make water. Carbon, well, you're not going to find carbon on that table because carbon is just an element. If you have an element already in their standard state, like solid carbon, then the enthalpy of formation is 0. All right, it doesn't take energy to have carbon in a standard state. It's the natural state. It doesn't release energy to have carbon in the standard state. You just find carbon that way in the universe. So hence, it's 0. So any element in their standard state will be 0. So you look for carbon monoxide, you look on the table, well, it is negative 110.5 kilojoules per mole, and there's your equation. You make carbon monoxide from carbon and oxygen. And lastly, you have hydrogen gas. Same story, it is an element in its standard state. Hydrogen is found as a gas. So of course, the enthalpy of formation will be 0. Right, so far, are you clear about how to pull up these equations? You just look on the table, you look at what is found in the reactant or product, look on the table, you copy the equation down, you look at the number, okay? All right, so you need to form this equation, and you have these. So now you can apply Hess's law. We learned this yesterday. We can flip-flop the equations. You can multiply them by a constant until they cancel to make the final net equation. And in order to do that, just take a look. Water is found as a reactant in your final equation, but water is found as a product in one of your givens. So you know you have to flip that one. You got to reverse the reactant and product, and if you do that, you got to change the sign of the enthalpy. So now instead of negative 241, you have positive 241. And if you take a look at the second equation, do you have to do anything with that one? No, because carbon monoxide is a product. Well, it is a product in the final equation as well. So you don't have to change it, just copy it down, do nothing. All right, so the standard enthalpy information of that will not change. It's still negative 110.5. The oxygen should cross out with the oxygen. You add them up. Boom, there you have it. Okay, you have water plus carbon. You get hydrogen gas and carbon monoxide. And you add up the enthalpies, you have positive 131.3 kilojoules per mole. This will be the answer to the question. What is the enthalpy of this reaction? It is 101.3 kilojoules per mole. Right, notice that we basically had no information. We just pulled that out of nowhere. Right? Well, we pulled it out of the table. So please make sure you have the table with you so you can answer questions like, well, what is the enthalpy of this reaction? Just use their formations and Hess's law. Does that make sense? So any questions? All right, cool.
State of the reactant and the products, the equations, we will be given or we have to decide it by ourselves?
Well, it'll be given. You will always have the states.
Okay, thank you.
Yes, that is not a problem. All right, so let's do example 2. I'll give you some time to work on example 2. You have another equation. So nitrogen dioxide becomes dinitrogen tetroxide. So for your convenience, so you don't have to flip the table, I already gave you the equation. Now you can find these on the table if it's not given to you. So you have the standard enthalpy of formation of both nitrogen dioxide and dinitrogen pentoxide. So use Hess's law and this to solve the problem. What is the enthalpy? All right, so I'll give you like around 5 minutes and I'll take this up. All right, so for this question right here, you're asked to solve for the enthalpy of this synthesis reaction. All right, you're given the enthalpies of formations of both the product and the reactant, and all you have to do now is manipulate these equations, add them up, so that you will get the overall net equation. So here is what you have. You want to make this look like the equation on top. And you notice that nitrogen dioxide appears in the reactant, and there's 2 of them. So that means you got to flip the top equation and multiply that by 2. And if you do that, you do the same thing to the enthalpy. You multiply by 2 and change the sign. So now from negative 33.2, you have negative 66.4. As for the equation on the bottom, you don't do anything. Okay, dinitrogen tetroxide is already on the right side, and you already have that. You don't change it. All right, so you just write it out as it is, so the enthalpy doesn't change, 11.1. You can cancel the 2 oxygens, they appear on both sides, and you can cancel the 2 nitrogens. And as a result, you can now add them up. You have 2 nitrogen dioxide becomes dinitrogen tetroxide, and if you add up the enthalpies after you manipulate it, you have negative 55.3 kilojoules. Okay, and that will be your final answer. Okay, questions? I know what you're thinking. I know I said yesterday that this will somehow make these questions easier, right? But you're thinking, wait, no, how does that make sense? Now it's more harder. It's more complicated. Last time, well, we had to do Hess's law. We do the equation flips, but we have the equations. Now you don't even give us the equations. We have to look at them on the table, write them down, and then do the flip. Isn't that more complicated? Well, yes, if you choose to do it this way. We don't have to do it this way. You don't have to do the equation flip-flop. You don't have to multiply and cancel. Okay, that's the annoying way. We could instead use this formula, and you get the same thing. So this is the enthalpy of formation equation. if you know all of the enthalpies of the individual formations, and you know you can rearrange them to add them up to the final equation, well, then instead of just actually doing it on paper, you can just apply this formula and just work with the numbers. So the total enthalpy of the reaction is the sum of all of the products minus the sum of all of the reactants. Of course, you have to multiply by the moles for the products and the reactants. So sigma means sum, and it represents mole of the substance. Delta HF is just enthalpy of each individual step, the enthalpy of formations. All right, so in other words, again, you multiply the moles of the enthalpies of the products, add them up, you subtract the products of the mole and enthalpy of the reactants. And if you do that, you should get the final answer. So let's actually try that with the equation this time. Same question. You have the synthesis of dinitrogen tetroxide from nitrogen dioxide. So instead of using Hess's law, we're going to use this. So plug in the numbers. You have 1 mole of the product. Okay, N2O4 has just 1 mole, so it's 1 mole. The standard enthalpy of formation of N2O4 is 11.1, as we determined earlier from the table. Okay, that's it. That's all of the product you have. So you don't have to add it to another number. That's it. Subtract all of the reactants. We have just 1 reactant, so 2 moles times 33.2. That would be the standard enthalpy of formation of NO2. So if you punch this in your calculator, you should get negative 55.3 kilojoules, which is exactly the same as how we did it with Hess's law. All right, so it is the same strategy, except with this, you can just use an equation. You can skip all of the equation writing and flipping and canceling. All right, so you decide how you want to proceed to get the answer. If you like Hess's law, you don't mind doing the extra work, go ahead. If you prefer this shorter mathematical way, you go ahead and go for it. All right, so it makes no difference. In fact, they're literally the same strategy, except with the formula, you just skip all of the manipulations of the equation. You go directly to manipulating the numbers. Okay, the overall result will be the same. So, with that in mind, let's do example 3. Example 3 is a long example. The next, 5 slides are basically just spaced for this example. So 2 parts. Part A, determine the standard enthalpy of combustion of methanol and octane. All right, so you have the 2 equations right there for methanol combustion and octane combustion. After you determine the standard enthalpy of combustion for both of them, part B, determine which fuel has greater standard enthalpy per gram. So I'm going to give you around 10 minutes for this. It's quite a long question. You can do this however you want. You could use Hess's law, or you could just use the equation. I don't care. But for both, you need enthalpy of formation. So whip out the table. I'll give you 10 minutes, and then I'll take up part A and part B. So first off, you have to determine the standard enthalpy of combustion for both methanol and octane. So let's break it up. Let's do methanol first. So this is part A, determining the standard enthalpy combustion of methanol. Well, from the balanced equation, you realize that you need to look up on the table the formation of all of the reactants and products. So the formation of methanol, oxygen, carbon dioxide, and water as a liquid. And if you look on the table, you will quickly determine that here are the 4 numbers. Now for oxygen, you will have 0, because oxygen is an element in the standard form. So of course it's 0. For water, make sure you're looking at the liquid water, not the water vapor. So it's negative 285.8 kilojoules per mole. And also, here's the key part. A lot of you may fall for this. Standard enthalpy of formation is the formation of 1 mole of a substance from the elements. So in your equation, you must have 1 mole of methanol. Because we're trying to determine the combustion of methanol, you have to have 1 mole. Okay, so you must divide everything by 2 so that methanol has a coefficient of 1. Then you can determine the combustion of methanol. So once you do that, and you have the numbers, you can find N from the coefficients and apply this formula. All right, so you would have, well, this ugly thing, the products, so 1 mole of carbon dioxide times the standard enthalpy of formation of carbon dioxide, okay, plus 2 moles of water times standard enthalpy of formation of liquid water. Everything in brackets because all of these are the products. The sum of this will then subtract the sum of the reactants. So 1 mole of methanol times standard enthalpy of formation of methanol plus 0 because oxygen has a formation of 0, so that's just 0. Right, and believe your calculator should be able to do this in 1 step. You put this in your calculator and you should have negative 725.9 kilojoules per mole. All right, so do we have any questions about that? All right, so notice that the enthalpy of combustion should have a unit of kilojoules. But since we're talking about standard enthalpy of combustion, this refers to 1 mole of methanol. So the kilojoule is actually kilojoules per mole because it describes exactly 1 mole. So they're in fact the same thing in this case. So we're going to use kilojoules per mole for more accuracy because it is 1 mole of methanol burns for negative 725.9 kilojoules. All right, so that's why the unit is per mole. Normally it should be just kilojoules, but because you have 1 mole, you literally just divide by 1 mole. You do the exact same thing for the octane. You find on the table, okay, octane, that is negative 250.1. Oxygen is 0, carbon dioxide and liquid water, none of those change. So the only thing that changes is really the octane. And of course, you have to divide the equation by 2 because we're talking about the combustion of 1 mole of octane. So you cannot have 2 moles. So divide by 2, so the octane will have a coefficient of 1. So you have this equation right here. Once you get this equation, you apply this formula. The sum of the products minus the sum of the reactants. So now we have 8 moles of CO2 times, well, enthalpy of CO2, plus 9 moles of water times the enthalpy of water. So that doesn't really change except the N changed. Subtract 1 mole of octane, which is negative 250.1, plus 0 because oxygen would have 0. You put this in your calculator and you should get negative 5,470.1 kilojoules per mole. All right, and we use kilojoules per mole instead of kilojoules because we are talking about the combustion of exactly 1 mole of octane, so this is kilojoule per mole. So are we clear on how to find enthalpies of combustion? You can just straight up look at the formation of all of these reactants and products, apply this formula. All right, so let's do part B then. You found the enthalpies of combustion of both methanol and octane. Part B says, which fuel has the greater standard enthalpy per gram? Now, the reason I kept the per mole is because of part B, because part B asks us to find the energy per gram. So I have energy per mole for methanol is negative 725.9 per mole. To convert into per gram, all you have to do is divide by the molar mass such that the mole and the mole will cancel. All right, and how would you find the molar mass? Well, just look on the periodic table. Methanol has 1 carbon, so 12.01, 1 oxygen, so plus 16, 4 hydrogens, so 4 times 1.01. So that will be the molar mass. And you punch this into your calculator per gram. So instead of kilojoules per mole, now it's kilojoules per gram. You have negative 22.65 kilojoules per gram. So for every gram of methanol you burn, that's the amount of energy you would release. All right. You can do the exact same thing for the octane. Negative 5,470.1 kilojoules per mole. You divide by the molar mass such that the mole and the mole will cancel. You have 8 carbons for octane, so 8 times 1.01. 18 hydrogens, so 18 times 1.01. So now the unit is kilojoules per gram. You put this in your calculator. You have negative 47.87 kilojoules per gram. So for every 1 gram of octane that you burn, you will release 47.87 kilojoules. This is obviously more energy than methanol. So therefore, the combustion of octane releases more energy per gram, which is not a surprise. We use octane as car fuels for a reason, because it has high energy. That's why we don't use methanol. Do you have any questions? So is it clear what we should do in order to calculate enthalpies given formation information? All right, so the last example for this lesson is in fact very difficult. Okay, this is a long question that makes you apply all of the knowledge you've learned in this unit so far. Here goes. So we have gasoline, octane, is burned in vehicles and is cooled by a coolant, ethylene glycol. So what mass of octane is completely burned to cause the heating of 10 kilograms of aqueous ethylene glycol automobile coolant from 25 degrees Celsius to 70 degrees Celsius? So the specific heat capacity of the ethylene glycol is 3.5 joules per gram per Celsius. And of course, you assume water is a gas when all of this is happening. And also, the heat flows directly into the coolant. None of them is wasted by the environment. Assume isolated system. This question is actually pretty short. The second paragraph is the question. All right, the other 2 paragraphs are just the assumption. So really, what mass of octane? That's the only thing you need to solve for. How many grams of octane do you have to burn to heat 10 kilo of ethylene glycol from 25 to 70 degrees? So you're not giving a lot of information here. If you're stuck, I'll give you a hint. Look at what the values are that are given to you. What can you possibly do with a difference in temperature, a mass, and a specific heat capacity? All right, so I'll give you around 10 minutes for this question. It's a 3-part question, so please try your best to get this. If you get this question, then you really learned this unit well. All right, I'll give you 10 minutes and then I'll take this up. All right, so this is a very, very tough question. When you try to do this, you may have realized you're not giving a lot of information to help you get to mass. So the first thing that jumps out at you is the fact that you have a temperature difference, you have a mass, and you have a specific heat capacity, and all of them belong to ethylene glycol. Okay, so this should bring back memories of the first lesson, Q equals to MC delta T. This is the only thing you can do at this point. Okay, you have all of the information needed to solve for the heat. So let's actually do it. So you can solve for the amount of heat gained or lost by the ethylene glycol. 10 kilogram is the mass of the solvent, but you cannot use kilograms. You must use grams because the specific heat capacity has it in grams. So you have to convert to grams by multiplying by 1,000. So multiply by the specific heat capacity, which is 3.5 joules per gram per Celsius, and multiply by the temperature difference, 70 minus 25. So putting this in your calculator, you should get this number. Something like 1.57500 times 10 to the 6 joules. this should have two sig figs, but we're not finished with the question. So I still need to use this number for a later calculation. So that's why I left 4 extra digits just to be safe. And because kilojoules is the unit we want for enthalpy, not joules, it's too small, just multiply by 1,000, you should have 1575 kilojoules. Now this is a positive number. It means that the ethylene glycol gained this amount of heat. This also means that the combustion reaction released this amount of heat because all of the heat, we assume, goes into the ethylene glycol. So that means the enthalpy of the octane will be the negative of this number. You just slap on a negative sign and you have the enthalpy of the combustion of octane. Okay, and by enthalpy, I mean like the entire enthalpy of burning all of that octane. So you have negative 1575 kilojoules for the enthalpy. Okay, so far so good. Here's the balanced equation for the combustion of octane. I don't believe this was given to you, but you have to come up with this on your own. And you just have to know that combustion is burning with oxygen and the product would be CO2 and H2O. Now, you can use the standard enthalpy of formation to figure out the standard enthalpy of combustion of octane. That means just for 1 mole of octane. Right now, we don't know how much octane we have, but if we can figure out what is the energy for 1 mole, and we know what energy we have, we can divide for the amount of moles. If you just look on the table, you would quickly realize, well, carbon dioxide is negative 395.5. We've used that number many times already in this lesson, and there's a mole of that. 9 mole of water, that is negative 241.8. Subtract the reactant, 1 mole of the reactant times negative 250.1, and oxygen is obviously 0. We've done this in the previous question and put it in. You have negative 5,074.1 kilojoules per mole. This will be the standard enthalpy of combustion of octane for 1 mole of octane. Okay, so we can now use this formula that we learned in a previous lesson. If you want to solve for the mass of octane, you got to know how many moles I have. N represents how many moles. So all you have to do is isolate for N. The total amount of energy burned, delta H for the octane, we just calculated. Also the standard enthalpy of combustion, we also calculated. So substitute those numbers in. All right, the total energy is negative 1575. The per mole energy is negative 5,074. So you divide them. How many moles do you have? Well, you have 0.310310 moles. All right, I left a ton of digits because I'm not finished. The question doesn't say moles. It says what mass, and mass refers to the SI unit, grams. It's actually kilograms, but we use grams. To convert between mole and grams, this is now a grade 11 chemistry problem. Just use stoichiometry, just convert using the molar mass. If you multiply by the molar mass of octane, 8 carbons, 18 hydrogens, the moles should cancel out. And finally, you will round to the correct number of sig figs, in this case 2 sig figs. Your answer should be 35. So therefore, if you burn 35 grams of octane, you will heat up the ethylene glycol, 10 kilograms of that, from 25 to 70 degrees. All right, finally, we arrive at the answer. So this is quite a difficult question, but this includes everything that we've learned. Q equals to MC delta T, delta H equals to negative Q, delta H equals to N delta H combustion. All 3 equations are used, and then you used the standard enthalpy of formation formula. All of them combined into this one question. So it's a really good question to practice with, to just hone all of your skills. And that will be it. This is for this class. We literally just learned one thing today. How to use the enthalpy of formation equation to solve for enthalpy without having to do the manipulation of the equations with Hess's law. All right, so once you know how to do this, you can now choose. Do I want to use Hess's law and write down all of those equations and flip them? Or do I want to apply the formula and get the same answer? That's up to you. Okay, on the test, I will just be looking at your final answers. So go ahead and pick your favorite way. There are perks to both methods. I find that more students like Hess's law just to write down the equations because I guess that's something you can see. It's very intuitive and logical. So many people do that, but this one is way faster. All you have to do is punch the numbers right and remember the formula correctly. So you go ahead and choose one. Do we have any questions? All right, so I'm going to end this one here.